Last week we discussed the definition of research. We define research as a systematic inquiry process to answer research questions by collecting data, managing data, analyzing data, interpreting the results, and report the results. So the one goal of research is to answer research questions. But it is not the ultimate goal of a research. The ultimate goal of a research is to build knowledge, to improve our knowledge of the human being. In the sense, to under this world, we have to understand the rules underlying this world. So we have to build our theory. And to build our theory, we have to develop some concepts with an abstract idea, a generalized abstract idea about a set of object, behavior, occurrence, attributes, so on and so forth. So this week we're going to focus on 3 items. First, we talk about definition of concept, hypothesis, proposition, and theory. And then we discuss what is a good theory, how to conduct an empirical research, the process of conducting research. And then we move on to the discussion of fundamental knowledge about empirical research. For example, we talk about what is a sample, what is a population, what is inferential statistic, what is discrete statistics, so on and so forth. So first, let's take a look at how researchers think, what is theory and what is concept, and how they're related to empirical data.
You know, the terms that we use in science are used very specifically in science as terms of art, but they have very different meanings on the street, and this is a source of a lot of confusion. When scientists talk about fact, they're talking about confirmed observations, and facts are interesting, but they're not terribly exciting. They don't do a whole lot for you. Facts are a dime a dozen. There's facts all over the place. A hypothesis is a testable statement. You're saying, you know, what's the relationship between this and this? And you go out and test it, and you either accept or reject your statement of that relationship. Hypotheses are very useful. They're very helpful. They help us build theory. Theories are the most important things in science. Theory to a scientist means explanation. And these are logical constructs of facts, of tested hypotheses, of laws, of all kinds of stuff that, taken together and put in a logical descriptive fashion, help us understand some kind of natural phenomenon. Most lay people think that theories are guesses or hunches or something that you don't have to take terribly seriously. It's not such a big deal. Completely opposite in science. Theories are the most important things in science. What a lot of unfortunately textbooks lead people to misunderstand is that a really good theory grows up into a law, as if theories are refined and then become laws, and laws are somehow more important than theories. In science, actually, what a law is a descriptive generalization. So we talk about the laws of thermodynamics that tell you about heat under different circumstances. You hear about the laws and study the laws of heredity that Mendel developed, the law of independent assortment and so forth, because theories explain laws. So in general, the hierarchy of explanation is very different in science than it is in the general public. The general public puts facts on top, laws next, hypotheses, and then theories. Maybe theories and hypotheses can move around a little bit. In science, on the other hand, theories are the most important thing. Laws are next most important. Hypotheses are next most important. And perhaps the least most important part of a scientific explanation is facts, because facts are a dime a dozen. And facts don't explain anything.
To say a few words about how science goes from making observations all the way to turning those observations into theories. And I'm going to naturally reflect my own field of geology. It began by people observing things that we see every day, like rivers, for instance, flowing. And people began to notice that big rivers tend to flow in big valleys. They notice that rivers get bigger downstream. They notice that when tributaries come into a mainstream, they generally make an angle that points upstream, and so on and so forth. These are observations. And after you make enough observations, you realize that these are scientific facts. It's not always true that they make an acute angle, but it's true enough so that when you find they do not make an acute angle pointing upstream, you know there's something happened. Something has happened of geologic interest there. So we have observations, and gradually they turn into facts. Somebody a long time ago noticed that the sun rose in the east and set in the west. And after a while, that becomes a fact, and we can be absolutely certain that tomorrow the sun is going to rise in the east and set in the west, and you and I would stake our life on that. Right? Right. But why? It appears that the sun moves around the earth. And Ptolemy worked out a theory that had the earth at the center of the solar system and the sun working around, revolving around it, and everything else, that lasted for many, many centuries and explained things pretty well, but not quite well enough. And so at some point, another person, Copernicus, got the idea that it might be the other way around, and maybe the sun is at the center of the solar system and the earth is going around the sun, and so are the other planets. And so there was an observation, it was a fact, but the hypothesis of Ptolemy, or you might even have to call it a theory since it lasted so long, was then replaced by another theory. So to get to a theory, you have to have something that explains all the known observations, the facts, that survives the test of time, that has predictions. Like if you accept Copernicus's theory, then you can predict the motion of the planets. And when you look at the motion of the planets, astronomers do that, they find that they meet much better than they did with Ptolemy's system, the observation. So science progresses from observation to fact, then some explanation, a hypothesis, and then once the hypothesis is supported, corroborated over and over and over, it becomes a theory. And we've seen this happen in geology where continental drift was rejected, rejected, rejected. Then suddenly, at one meeting almost, one scientific meeting, it was accepted in a new form, plate tectonics. This was about 40 years ago. And plate tectonics is now a very strong theory. It's been around 40 years. Evolution has been around for 150 years or so. And no one has ever disproven it. If it's wrong, why can't it be shown to be wrong? It may be wrong. Someone may show it wrong tomorrow. Someone may disprove or falsify plate tectonics. I would be totally shocked and amazed, but I have to admit as a scientist that it's possible.
A fact is actually the most trivial construct in science. It's an observation. We say sometimes it's a confirmed observation, but if somebody else doesn't confirm it, which is often the case, it's really just a reported observation. And that's fine. Maybe it's wrong later on. And people sometimes think it's weird that a fact can be wrong, then it's not a fact. Well, that's right, but facts can be wrong. They're just pieces of data. A hypothesis is more complex. It's a proposition about how something works in the world that you generally propose after you have some hard evidence, after you have gathered some facts, and you want to propose something to explain it or to explain something else related to it. And the hallmark of a hypothesis is you have to test it somehow. You have to be able, in principle or in practice, really, to find some evidence that would work for or against it. Maybe you can't do that exactly now, but at some point it is testable in the natural world. If it's not a scientific hypothesis. Now, a theory, of course, the word that everyone confuses, people think it's what scientists dream up after they've had too much coffee too late at night. Yeah, we can get like that, but that's not what a theory is in science. And this is the scientist's fault, because many scientists talk as if a theory is just some kind of wild idea. That's not the way they should use the word. And when they use a word like that, either they're just fooling or they're not thinking seriously, because that would never be called a theory in any science. A theory is the strongest construct in science. It actually is a body of knowledge that purports to explain some major body of fact, hypothesis, some big component of a natural science. Plate tectonics is a theory. Evolution is a theory. Natural selection is even a theory because there's so much involved in natural selection. It's very complex. A theory is not liable to be slain by a single fact. It can be changed a bit, and we change our theories all the time, the body of work that's in it. But we very seldom falsify theories based on things like this. Now, a law is also another word that's used in a lot of different sciences and in different ways. And I would defer on that to people who actually are in sciences where laws are used, because in many sciences the term law is simply not used. If in some sciences it's an equation, or it reduces to an equation, then it should be called an equation. If in other sciences it reduces to a tautology, that is, it's simply restating what its premise is, then it should be called that. But if the law is a feature of nature that is inviolable, a lot of people think that's what a law is. But this depends on the discipline. Whereas theory is not like that. Theory is just a large construct of explanation of the natural world.
Okay, most frequently when I'm talking to young Earth creationists or anyone else of, frankly, any sort of opinion on the matter, usually makes a key misrepresentation of a couple words, and in fact, the entire method of science. So today I'd like to address the definition and the exact meaning of what this is. So the first thing I'd like to talk about is the scientific theory in and of itself. What is a theory? And what is a hypothesis? And what is the difference between the two? Now, in popular usage, a theory is just a vague and fuzzy sort of fact, and a hypothesis is often used as a fancy synonym for guess. But to a scientist, now, a theory is a conceptual framework that explains existing observations and predicts new ones. For example, suppose we see the sun rise. This is an existing observation which is explained by theory of gravity proposed by Newton. This theory, in addition to being explained why we see the sun cross the sky, also it explains many other phenomena, such as the path followed by the sun as it moves, as seen from Earth, across the sky, the phases of the moon, the phases of Venus, the tides, just to mention a few. You can today make a calculation and predict the position of the sun and the phases of the moon and Venus, the hour of maximum tide, all 200 years from now, for example. Now, a hypothesis, on the other hand, is essentially a working assumption. Typically, a scientist will devise a hypothesis and see if it holds water, per se, by testing it against available data obtained by previous experiments and observations. If the hypothesis does hold water, the scientist declares it to be a theory. Now, the process where we get from our general assumption or a hypothesis to a generally accepted scientific theory is through the scientific method. The scientific method is the best way yet discovered for winnowing the truth from lies and delusion. The simple version looks something like this. First, we make an observation, some aspect of the universe. Let's say, when I drop a ball, it will fall. Now, we're going to invent a tentative description called a hypothesis. That is consistent with what you have observed. I've dropped a ball, and in fact, it did hit the ground. So we're going to use this hypothesis to make predictions. If I drop a ball again, or in fact, let's say I drop an apple from a tree, it will hit the ground. It will not just float in thin air. Now, the next step is to test those predictions by experiments or further observations and modify the hypothesis in light of your results. So, let's say we observe an apple falling from a tree. It hits the ground. Or, in fact, as Isaac Newton very conveniently found out, it hit him in the head. Obviously, we know this is a little bit of a analogous story, per se, because we don't know if exactly even this, yeah. Now, we observed the apple falling from the tree, so we do many, many, many more experiments, and in fact, we control this by removing outside factors such as wind resistance, any sort of magnetic field, to make sure that, let's say, the ball that we're dropping is not magnetic, or the surface we're dropping it to is not magnetic, or it's not affected by the magnetic field outside, maybe the magnetic field of the Earth. So we're talking about the individual gravity. So we're going to repeat these steps of using the hypothesis to make predictions and continuing to test these predictions until there are no discrepancies between the theory and experiment and or observation. So what we have decided here is the theory of gravity. For example, if I drop a ball, it will hit the ground. It will go down towards the gravitational pull of the Earth. Now, when consistency is obtained, the hypothesis becomes a theory and provides a coherent set of propositions which explain a class of phenomena. A theory is then a framework within the observations are explained and predictions are made. So now we can use our theory of gravity to make predictions about future balls that we're dropping, or any other matter for that effect that would be pulled in with any sort of gravitational pull with the Earth. Now, one would find it interesting to say that this theory that we just came up with through this sort of experiment.
Alright, from the above two videos, you have learned a little bit about what is concept, what is theory, and what is hypothesis. And now in this slide, I'm going to summarize the relationship between them. The relationship between observables, concept, hypothesis, and theory. So let's start with the observations of objects. That's the observable or the fact or the data we use for our empirical research. That's the empirical level. That's what we can feel about this world. But we need to develop concepts based on what we observe, what we feel. And then we have hypothesis and theory, both of which is above the abstract level of concept. Concept is very important. It's also called construct. It's the basic building block of theory development. It's the generalized idea about classes of objects, attributes, behavior, occurrence, and process that have been given a name. For example, management is a concept. It is constructed by human being and it has been given a name to describe the behavior of a set of behaviors. And then leadership is also a concept. It's a construct by human being. Proposition and hypothesis are both built on concept. A proposition is a statement concerned with the relationship between concepts. It observes the universal connection or logical linkage between concepts. For example, we can say smoking is injurious to health is a proposition because now we have two concepts, smoking and health. And the relationship between these two concepts is smoking is injurious to health. So this statement states the connection between these two concepts in a general way. So it is a proposition. And proposition is at higher level of abstraction than concept. So it's abstract and built on concepts. And hypotheses are propositions that are empirically testable. Proposition may not be directly testable because some concept cannot be directly measurable. And to make a hypothesis testable, you have to make all the concepts measurable. For example, here, for the smoking is injurious to health, as a proposition, we can transform it to a hypothesis by hypothesize that a smoker has a higher probability of getting lung cancer. So this is a testable statement. We can collect the data of whether a person is a smoker or not. We can also collect the data of how likely whether this person would get the lung cancer. So we can test the relationship between these two concepts and make this statement testable. So it is a hypothesis. Now if we make it testable. Now what is theory? Theory basically is a coherent set of general propositions. We can use it as a principle to explain the relationship of certain observed phenomena. For example, how can we explain how the market price of the product is determined? And then we have a theory that the market price is determined by its supply and demand. And this is a theory that we use to explain how the price is determined, and it contains a set of general propositions. For example, we can say holding the demand constant, the higher the supply, the lower the market price of a product. We can also say that holding supply constants, the higher the demand, the higher the price. So those two propositions are consistent, are coherent with each other, and consistent with the hypothesis that market price is determined by the supply and demand. Now I want you to do in-class practice by developing some propositions from the theory we described in this slide. The social exchange theory was introduced in 1958 by sociologist George Homans. And this theory proposed that social behavior is the result of an exchange process, and the purpose of this exchange is to maximize the benefits and minimize the cost. Based on these theories, what type of proposition can we develop? I want you to stop this video, leave it for maybe 5 minutes. Think about that based on this theory, what kind of proposition or hypothesis we can develop. Now here's some example that we can develop the proposition based on the social exchange theory, which proposed that the purpose of the social exchange is to maximize the benefit and minimize the cost. First example would be individuals choose those alternatives from which they expect the most profit. Or second, cost being equal, people would choose alternative from which they anticipated greatest rewards. Or rewards being equal, they choose alternative from which they anticipate the fewest cost. So on and so forth. Now we have to understand what is a theory and how it's related to hypothesis, concept, and observable. Now, we need to go further to understand what is considered a good theory. According to Stephen Hawking, in his A Brief History of Time in 1988, he said, "A theory is a good theory if it satisfies two criteria. It must accurately describe a large class of observations on the basis of a model that contains only a few arbitrary elements. And second, it must state definite predictions about the result of future observations. The second part of this statement is easy to understand. It simply said a good theory, should have predicting power. How about the first part? The first part, he said, accurately describe of the large class of observation. That means that it must be consistent with the reality. It can be used to explain the world, explain the observations. And it's on the basis of a model that contains only a few arbitrary elements. That means that it has been generalized. It's based on the abstract model. Based on above discussion, we can state that this theory is a good theory if it satisfies the following three criteria. First, it is objective. That means that the statement can explain the observables. It's consistent with the reality. The second is verifiable. That means that it can be tested using the evidence, using the reality, using data. And third, it is falsifiable or disprovable. And some statements, for example, tautology, they are not falsifiable, will never be wrong, so it can never be disproved. For example, a statement that a white horse is a horse. That must be true, because that's a tautology. So this statement is not a good theory because it cannot never be falsifiable. And the other example of an undisprovable statement would be some moral questions. Okay, whether it's good or not questions. If it's involve the value judgment or moral judgment, then usually is not disapprovable or falsifiable. So it cannot be a good theory. Cannot be a theory actually. Now let's talk about the reasoning approaches that link theory and observation to reality. We have two reasoning approaches. One is called the deductive reasonings. Deductive reasoning approach starts from theory, and based on a theory we develop hypotheses, and then we collect the data based on the reality observations, and then we test the hypothesis. If the hypothesis is supported by the observations, then your examination confirms the theory. If the hypothesis is rejected by the observation, then we reject the theory. So this approach is the reasoning that the quantitative empirical research is based on. Usually we start from the theory, and based on the theory we develop a set of hypotheses, and then we try to test it to see whether the hypothesis is correct or not. The reasoning sequences can also go the other way around. We can start from observation, and then we observe the underlying pattern and develop tentative hypotheses, which can be further developed to theory. And this is the approach usually used by qualitative analysis, which usually based on small cases, small observation of documents, and then based on the small number of cases, we observe the underlying pattern, which can be further developed to a theme. And inductive reasoning and deductive reasoning can supplement each other. And actually, you can view these two reasoning sequences as a cycle. We can start from few observations, then develop a hypothesis, and a theory, and further we collect more data, a larger sample of data, and then use this larger sample to test whether the tentative theory we developed from a few cases is supported by larger number of cases or not. Now let's talk about the research process, the steps of conducting an empirical quantitative analysis. Usually we start with a very broad topic. For example, we just know that we are interested in public financial management, or more specifically we're interested in sales tax, or we're interested in organization theory. But we don't have a very specific idea about what exactly our hypothesis is, our research question will be. What we can do is to conduct a literature review to help us to narrow down and focus in. So we can conduct a review of previous study to see what previous studies have done, what they say about this topic. So that helps us to narrow down our topic, then we can focus in and develop our research question. And after we identify our research question, then we need to make our concept measurable. And that's the process of operationalization and conceptualization. Then after operationalize our concept, we will have a hypothesis that can be testable. And then after we have our hypothesis, we need to decide or select the appropriate research methods, collect the data, analyze the data, and finally draw a conclusion. So that's basically the whole process of conducting empirical research. And now let's focus on each of these steps and talk about this different process a little in more detail. The first step for the research process is literature review. We have a lot of reasons that we want to conduct a literature review before we go further into our research. For example, we want to make sure that our research question will have some contribution. We're not repeating what others have done. So we need to examine what has been examined and what yet to be explored. And we can do the literature review to achieve this goal. And literature review also help us to identify data sources that other researchers have used. So you don't have to waste the time to Google the data you need for your research. You can also use literature review to develop general explanation for observed variation in the behavior of your numbers. Or you can use literature review to identify potential relationships between concepts and to identify researchable hypotheses. And earlier we said inductive reasoning start from theory. And start from theory to hypothesis to observation, and then use observation to test the theory. So to use this reasoning approach, you have to find out a theory that has been proposed by previous studies, and then you use your data, you collect the data to test this hypothesis, to test the hypothesis developed from this theory. And you can also use literature review to learn how others have defined and measured key concepts. As we discussed earlier, to test a hypothesis, the concept contained in the hypothesis has to be clearly defined and measurable. And literature review can help you to see what others have defined this concept and measure this concept. For example, if you want to examine how employee empowerment affects client satisfaction, then you have to understand what employee empowerment means and how to measure employee empowerment before you can go further into your research. And conducting a literature review can help you to achieve this goal. And you can also use literature review to help you to decide your research approach or select the appropriate approach. After your literature review, you probably have a much better idea about your research question. And there's some general guidelines for stating your research questions, research problems. And always state your problem clearly and completely. Instead of thinking it in your mind, in your brain, write it down on the paper, and in a clearly and complete fashion. And at the same time, when you state your problem, always think about the feasibility of the project and whether your problem can be answered, whether you have the data needed to answer this research question. And make sure your question is exactly what you try to convey. An example of an answerable question can regular exercises reduce an individual's cholesterol level? Okay, now if you have the data of cholesterol level of a sample of individuals, and if you can ask whether they have regular exercising or not, then this question can be answered, and this problem is stated clearly and completely also. So it is an answerable research question. After you define your research question, the next step for you is to operationalize the variables that you need to examine in your research questions. So you need to translate theoretical concept into observable information that can be gathered on unit of analysis. There are two criteria you need to use to evaluate how good your measure is. Okay, one is that how valid are your measures. The second is how reliable are your measures. We're going to discuss this in more detail next week. So basically we are focused on operationalization and conceptualization of variables next week. And now you just need to understand that after you define your research question, you need to make your concepts measurable. You need to define and measure your research question. Before you can collect the data, you have to decide what level of application your hypothesis should be observed. In other words, you need to select the unit of the analysis, the observation level. Okay, it could be individual level. For example, if you focus your research question on clients or leaders, individual leaders, they are on individual level. So your observation would be based on citizens, based on leaders, so on and so forth. It can also be groups. For example, it can be organization, it can be company, it can be firms, it can be counties, it can be cities. It can also be a country level. US, Canada, OECD countries, so on and so forth. After you collect your data, the next step for you is to choose the method of research. Okay, you can choose qualitative data analysis versus quantitative data analysis, or you can choose a mixed approach that contains both qualitative data analysis and quantitative data analysis. And under the quantitative data analysis, you can also either use descriptive data analysis or inferential statistics, or you can use both. Now you have defined your research question, you have identified your analysis unit, you have chosen the appropriate research approach. The next step for you is to collect your data. There are two types of data sources you can use. The first is called the second data sources, which you use the data you collected by others. Or you can collect your own data set. You can use experiment, you can use survey, you can use other type of data collection approaches to collect your own data. And sometimes you want to combine these different data sources together. For example, you can use the survey to collect the parent information in the school district. You can also use the second data sources to supplement this survey data. For example, you can supplement the data set of the school district by looking at the property tax rate of the school district, for example. You should also need to identify the population that you want to generalize the conclusion to. And you also need to determine how you can reach the population to draw a sample. And if a random sample is impossible or inappropriate, you need to decide how you can avoid the non-random selection bias that caused by the non-random selection. Now you can start analyzing your data. And when you analyze your data, try to make sure your analyze technique is transparent and replicable so that others can follow your research method without much problem and can replicate your research if they would like to. And also think about how to present your results in the most meaningful way possible so that your readers can understand your conclusion and your analysis and your results. And also that a clear and meaningful result presentation is always more persuasive and more widely read. Always keep in mind that the one goal of your research is to answer the research question. So if everything written in your report should be around your research question. If your research question is not answered, that is not good research. That's not acceptable research actually. So always draw back, connect analysis back to the puzzle and your hypothesis, your research question, and what the results suggest, what the analysis suggests to the research hypothesis and the research question. Does it reject the hypothesis, reject the theory or not? Always connect it back to the hypothesis.